Right now, somewhere in the universe, an invisible wave of silence is haunting humanity. It's not a supernova or a black hole. It's something even more chilling. Despite living in a galaxy of over 400 billion stars, we have never received a single confirmed message from another civilization. Think about that. This cosmic silence terrifies scientists more than any gamma-ray burst, because it suggests there's something deeply wrong with how we understand life in the universe. Let's start with the numbers. Our galaxy, the Milky Way, is more than 13 billion years old. That's plenty of time for countless worlds to form, evolve, and birth intelligent beings. And even if only 1 in every million stars harbors an advanced civilization, we should still expect at least 400,000 alien societies out there. And yet, we hear nothing. Imagine walking into a city that should be teeming with millions of people, but every street is empty, every light is off. No sound, no life, just silence. That's what we're facing. This mystery has a name, the Fermi Paradox, named after physicist Enrico Fermi, who asked the haunting question that still echoes in laboratories and observatories. Where is everybody? The question may sound simple, but its implications are anything but. If intelligent life is common in the cosmos, then something is stopping them, or us, from communicating, expanding, or surviving. Some propose that we are alone, a solitary miracle in an otherwise lifeless universe. But others suggest something far darker. What if there were civilizations, and something wiped them out? Enter the concept of the Great Filter, a barrier, somewhere along the path from basic biology to interstellar empires, that few or no civilizations manage to cross. Maybe life itself is rare, or maybe intelligent life always destroys itself before it spreads. This idea sends a shiver down the spine. Because if the Great Filter lies behind us, then we're special, survivors. But if it lies ahead, then our time may be limited. Nuclear war, runaway AI, environmental collapse, galactic pandemics. Each one could be the silent killer of civilizations, including ours. But let's go deeper. Some theorists suggest that civilizations remain quiet on purpose. According to the dark forest hypothesis, the universe is like a dark forest. Each civilization is a silent hunter, afraid to reveal itself, because any sign of life could attract a predator. Imagine broadcasting your location into a jungle filled with unseen hunters. Not smart, right? That's why, in this vision of the universe, everyone stays quiet. Not because no one's out there, but because everyone's afraid. Could this be the real reason behind the silence? Or maybe we're not looking in the right way. Most of our searches for alien life, like SETI, rely on radio waves or light signals. But what if advanced civilizations use technologies beyond our comprehension? Quantum communication, neutrino beams, gravitational waves. To them, our primitive instruments might be like using a flashlight to detect Wi-Fi. There's also the possibility that alien life is here, but unrecognizable. Not carbon-based, not biological, not even physical. What if advanced beings evolved into artificial superintelligences and now roam the universe as energy patterns, hiding in black holes or existing in other dimensions? And yet, despite the silence, we continue to search. We build new telescopes, scan exoplanets, decode strange signals, and send our own probes into the void. Because the truth is out there, and we must find it, or be found. In this quest, we're not just asking, where is everybody? We're also asking, what will become of us? Will humanity break through the Great Filter? Will we join the cosmic conversation, or become another silent ruin in the dark? Only time and science will tell. But until then, the silence remains, and it speaks volumes. Imagine a force, invisible, untouchable, and yet holding the entire universe together. Scientists estimate that 85% of the matter in the cosmos is completely invisible to us. It doesn't emit light, it doesn't reflect it, and it doesn't interact with any of our instruments. We call it dark matter. But truthfully, that name barely scratches the surface of its mystery. If dark matter didn't exist, galaxies would spin apart like leaves in a storm. Stars wouldn't cluster, planets wouldn't form. Life, as we know it, would never emerge. In fact, the entire cosmos would be a thin, cold mist of scattered atoms, drifting forever. Let that sink in. Everything we see, from majestic galaxies to our own bodies, is just 15% of the universe. The rest? A ghostly presence that shapes everything but refuses to be seen. This is not science fiction. This is physics, and it's terrifying. We've built enormous detectors deep underground, shielded by mountains, to search for the faintest whisper of dark matter. We've looked in space, in particle accelerators, in ancient stardust, and yet, nothing. It's like trying to catch a shadow with your bare hands. But what if dark matter isn't just out there? What if it's something more sinister? Some physicists believe dark matter may be a signal from a hidden realm of the universe, a dark sector with its own particles, its own forces, even its own galaxies. A mirror cosmos, ghosting our own, only interacting through the gravitational echo we feel in the stars. Others suggest something more radical. What if dark matter is a sign of higher dimensional physics, like strings vibrating in multiple dimensions beyond our own? What if we are only seeing the shadow of real phenomena unfolding in realms we cannot perceive? This idea breaks the limits of our imagination, and yet the math supports it. And dark matter isn't the only ghost we chase. There's something even more elusive, something that doesn't just shape the universe, it drives its expansion. We call it dark energy. In the late 1990s, scientists discovered that the universe isn't just expanding, it's accelerating. Galaxies are being pushed away faster and faster, like they're riding on an invisible tide. But what's fueling this runaway expansion? Dark energy. It makes up nearly 70% of the entire cosmos. Combined with dark matter, that means 95% of the universe is made of stuff we can't even see. We live in a universe where the known, all the stars, planets, and life, is just a glowing speck in a sea of darkness. So how do we live in such a universe and still understand our place within it? Some see it as humbling. Others see it as exhilarating. Because in the face of the unknown, we do what humans do best. We explore. We ask questions. We build instruments. We invent mathematics to describe what our eyes cannot see. We listen to the gravitational hum of the cosmos, hoping to catch a glimpse of its invisible soul. And maybe, just maybe, dark matter and dark energy are not our enemies. Maybe they are the next great adventure, the next frontier, the whisper of truths that could redefine everything we believe about existence. The universe, it turns out, isn't just darker than we imagined. It's stranger. And the more we learn, the more we realize we've only just begun. Imagine waking up one morning to find the sky turned brown, the oceans poisoned, and the air itself deadly. This isn't the plot of a sci-fi movie. It's the terrifying reality of a gamma-ray burst, one of the most powerful and destructive events in the universe. If a gamma-ray burst, or GRB, were to strike Earth from a nearby galaxy, the consequences would be catastrophic. And worse, it would happen without warning. In an instant, the powerful wave of gamma radiation would slice through our atmosphere, stripping away the ozone layer in seconds. That vital shield, which protects all life from harmful solar ultraviolet rays, would vanish. Suddenly, every living thing would be exposed to a relentless barrage of UV radiation from the sun. But it wouldn't stop there. The atmosphere would react violently. The gamma energy would trigger a series of chemical reactions, producing vast clouds of nitrogen dioxide, the gas that gives smog its dirty brown color. Our once blue sky would turn toxic. Rain would fall, but not the kind that nourishes life. This rain would be laced with acid, burning forests, contaminating fresh water, and killing marine life by the billions. And just when you think it's over, it's not. Trailing the initial gamma flash would be a flood of high-energy particles, a deadly particle beam that could bombard Earth for hours or even days. With the ozone layer already gone, this would prevent the planet from healing, compounding the destruction and ensuring that recovery is all but impossible. If any life managed to survive the first strike, it would soon perish in a world bathed in radiation and cloaked in poison. So, how likely is this? According to scientists, gamma-ray bursts powerful enough to threaten Earth happen in our galaxy about once every few million years. That might seem rare, but consider this. Mass extinctions on Earth, like the one that wiped out the dinosaurs, also happen on a similar timescale. Could a GRB have caused one of these extinctions? We don't know for sure, but some researchers believe a gamma-ray burst may have triggered the Ordovician extinction 450 million years ago, one of the deadliest events in Earth's history, when 85% of marine species vanished. And unlike asteroids, GRBs leave no crater. Their damage is atmospheric, making them even harder to trace. They are silent assassins from across the galaxy. Even worse, we have no defense, no warning system, no way to shield the planet. We might never see it coming. All we can do is study these bursts from afar, observe their brilliant, deadly flashes in distant galaxies, and hope that one never turns its aim toward us. They remind us that the universe is not only majestic, but merciless, that while we gaze at the stars with wonder, those same stars could, without a moment's notice, become weapons of mass extinction. And yet, even in the face of such terrifying forces, we continue our search. We map the skies, we catalog threats, we learn how the universe works, because knowledge is our only shield. The more we understand these cosmic death rays, the more we prepare for the unexpected, and the more we appreciate the fragile miracle that is Earth. In the darkness of space, survival isn't guaranteed. But awareness, that might just be our greatest weapon. Out in the dark, silent, undetectable, are forces capable of tearing entire solar systems apart. We're talking about rogue black holes, massive objects so powerful, so stealthy, that they could be passing right through our cosmic neighborhood without us even noticing. Astronomers estimate that a rogue black hole might pass within just 1 light-year of Earth every few million years. That might sound like a comfortable distance, but in astronomical terms, it's terrifyingly close. Close enough to disrupt the gravitational balance of our solar system. Close enough to pull planets from their orbits or send Earth hurtling into deep space. Imagine our world, slowly drifting away from the sun, temperatures dropping, atmosphere freezing, life vanishing, all because of a visitor we never saw coming. We live in a cosmic shooting gallery, and the bullets? They're invisible. They travel for millions of years, only to strike without warning. Right now, several rogue black holes could be passing silently through our solar system. We wouldn't know until they began to distort planetary orbits, or worse, tear entire worlds apart. This terrifying possibility drives astronomers to constantly scan the skies, hunting for gravitational ghosts that betray the presence of a predator. But here's the challenge. Black holes don't emit light. They don't reflect it. They don't shine. They are, quite literally, holes in space, swallowing everything, including photons. We can only detect them indirectly, by observing how they affect nearby stars, how they warp light, or how they cause background galaxies to appear distorted through a phenomenon called Gravitational lensing. Detecting a rogue black hole moving alone through space is like trying to find a single shark in the ocean without radar at night. It's one of the most difficult problems in modern astronomy. But it's not just theoretical. In 2022, scientists confirmed the existence of a free-floating black hole in our galaxy, a lone wanderer, born from a supernova, no longer tethered to a star system. It's real, it's moving, and it could have siblings. So what would happen if one of these rogue black holes entered our solar system? The first sign might be a subtle shift in Neptune's orbit, then Uranus, then Saturn. The planets would begin to dance erratically, pulled by an unseen hand. Eventually, Earth's orbit could destabilize. We might plunge into the sun, or be flung into the freezing void. Even if the black hole didn't collide with Earth directly, its gravitational influence could trigger global chaos. Tides would shift, seasons could warp, satellites would fail. Our calendars and clocks, built on the stability of planetary motion, would no longer make sense. Life would be thrown into disarray, all because of something we couldn't see. And the worst part? There's no way to stop it. No defense, no shield, no warning system. Our best chance is early detection, catching the gravitational whispers of a rogue black hole before it gets too close. But that requires technology we're still perfecting, and a lot of luck. In the grand scheme of the cosmos, we're like a village built next to a minefield, mostly safe, but never far from danger. The more we learn, the more we realize how fragile our place is in the universe. But that realization is also a gift. It drives us to explore, to build better telescopes, to map the stars, to understand the forces around us, and maybe one day, to move beyond Earth and plant our roots in multiple worlds. Because as long as we stay in one place, we remain vulnerable. And the universe? It doesn't play favorites. One day, our sun will die. It will swell into a red giant, a monstrous ball of fire that will engulf Mercury, Venus, and possibly Earth itself. Oceans will boil, mountains will melt, and everything we've ever known will vanish in a final blaze of light. But that's only the beginning. The true tragedy of the universe unfolds not in explosions, but in silence. Our sun is what scientists call a middle-aged star. It's about halfway through its 10 billion-year life cycle. Like all stars, it survives by fusing hydrogen into helium, releasing energy in the form of light and heat. But when the fuel runs out, the fire goes out. Now imagine a star that burns so slowly, so efficiently, that it could shine not for billions, but trillions of years. These are the red dwarfs, the slow-burning embers of the cosmos. They are the most common stars in our galaxy, and also the most patient. Some of them could live up to 100 trillion years. Let that number sink in. It's a timescale that dwarfs the entire history of the universe. These stellar marathoners will be the last lighthouses in a universe that grows darker with each passing eon. Even after our sun has long since faded, even after the last massive star has exploded in a brilliant supernova, these quiet red dwarfs will remain, glowing softly in the eternal night. But math is cruel, and even the most efficient fuel can't last forever. In 100 trillion years, the last red dwarf will burn its final hydrogen atom and die. Not with a bang, but with a sigh. It will cool, fade, and become a cold, dark remnant, invisible to the naked eye. At that moment, the universe will enter a new era, a time known as the degenerate era, where no new stars are born, and the night sky is completely black. No starlight, no warmth, no energy, only dead stars, black holes, and frozen planets drifting silently through the void. It's a future that feels less like science and more like poetry, a slow, melancholic unraveling of everything bright. But perhaps the most haunting part? It's not that the universe ends in fire. It ends in darkness. No final battle, no closing curtain, just an infinite stretch of time where entropy wins, where the last light goes out. And yet, there's something profound about this vision. It reminds us that everything is temporary, even the stars, that the most eternal-looking things we see in the night sky are themselves fleeting. But in that impermanence, there is also beauty. Because we exist in the age of light, a rare window where stars shine, galaxies spin, and life can wonder about its own existence. We are witnesses to a brief, blazing moment in the universe's grand timeline. And that's a gift. So next time you look up at the stars, remember, they are not just lights in the sky, they are stories. They are time machines. They are the brief flickers of brilliance in a universe destined for quiet. And we are here to witness them. Imagine a wave, silent, invisible, and unstoppable, sweeping across the cosmos. Not a wave of fire, not a wave of war, but a wave that rewrites the laws of physics themselves. This is not fiction. It's a possibility born from real quantum theory, a terrifying idea known as vacuum decay. According to modern physics, the universe as we know it might be living in a false vacuum, a fragile state that only appears stable. But hidden underneath is a deeper, more stable form of reality, the true vacuum. And if that true vacuum ever emerges, it would form a bubble, a quantum ripple, and expand at the speed of light, destroying everything in its path. No warning, no escape, no defense. Because the bubble travels at light speed, no signal can outrun it. The moment you realize it's coming, it's already here. And the horror doesn't stop with destruction. This isn't just annihilation, it's transformation. When the edge of the bubble reaches a star system, it would act like an invisible blade, slicing through space, instantly altering the fundamental forces that govern matter. Gravity, electromagnetism, the strong and weak nuclear forces. They would all shift, like flipping the settings on the universe itself. Within a microsecond, the electromagnetic force, which holds atoms together, could change in strength. Electrons might spiral into atomic nuclei or fly away entirely. Molecules would disintegrate. Chemical bonds? Broken. Matter? Unstable. DNA? Completely unraveled. Not from heat, not from radiation, but because the very rules that hold it together would no longer apply. Life wouldn't burn. It wouldn't scream. It would simply stop. Not just Earth, not just our galaxy, but everything the bubble touches. Planets, stars, black holes, light itself would all be remade by a new set of physical laws. A universe rewritten. Maybe the new physics would allow life again. Maybe it would be a peaceful realm. Or maybe it would be a cold, sterile emptiness forever. And here's the truly chilling part. We would never know it was coming. Right now, as you watch this video, a vacuum decay event could already be on its way, from billions of light years away, moving toward us at the speed of light. And there is nothing we can do. No telescope can see it. No satellite can track it. No technology can stop it. This is the purest existential threat imaginable. A reminder that the universe doesn't owe us survival. That even the most fundamental laws of nature are not written in stone, but in shifting quantum sand. But before despair sets in, there's perspective. The odds of vacuum decay happening soon are astronomically small. In fact, most physicists agree it's more likely to occur in trillions of years, if ever. Still, the idea matters, because it shows how fragile reality truly is. And it reminds us of a profound truth. We live in a universe that is still becoming, still shaping, still shifting, still dangerous, but still wondrous. We are fortunate to exist in this delicate window of physics, light, and life. And while we may fear the silent end, we should celebrate the vibrant now. We often think of the sun as a source of warmth, life, and light. But what if, one day, it turned against us? What if the same star that sustains life on Earth suddenly unleashed a storm so powerful it could cripple our entire civilization? This is not science fiction. It's a very real and very terrifying possibility. We're talking about a solar superstorm, a massive explosion of energy from the sun known as a coronal mass ejection. These ejections hurl billions of tons of charged particles into space, traveling at millions of kilometers per hour. When aimed at Earth, they can slam into our planet's magnetic field like a cosmic sledgehammer. The result? Electromagnetic chaos. Our modern world runs on electricity, satellites, power grids, internet cables, communication networks. Everything depends on a delicate, interconnected web of signals and energy. Now imagine that web being shredded. Power plants would fail. Transformers would fry. Entire regions could go permanently dark. No electricity, no water treatment, no sewage systems, no refrigerated food, no hospitals, no internet, no supply chains. Modern life gone in an instant. And this isn't just a theory. A 2008 study by the U.S. National Academy of Sciences estimated that a solar storm of sufficient intensity striking North America could cause over $2 trillion in damage, with full recovery taking years, not months. And that was over 15 years ago. Today, we're even more vulnerable, because the more we connect, the more we depend on systems that can be wiped out in a flash. It gets worse. High above us, hundreds of satellites orbit Earth, providing GPS, weather data, global communications. During a superstorm, these satellites would be bombarded by high-energy particles. They would fry in orbit, falling silent like dying stars. And on the ground, airplanes would lose navigation. Emergency services would go blind. Financial systems would be thrown into chaos. All because of a temper tantrum from our own sun. In fact, it's already happened once. In 1859, Earth was struck by the Carrington event, the most powerful geomagnetic storm ever recorded. Telegraph lines sparked. Paper caught fire. Auroras were seen as far south as the Caribbean. But back then, we had no satellites, no internet, no electric grid. If that same event happened today, the consequences would be catastrophic. And here's the twist. We might only get a 12 to 18-hour warning. That's all the time we'd have to shut down satellites, protect transformers, brace for impact. But in a world that runs minute by minute, would we be ready? Right now, scientists monitor the sun 24/7, watching for the signs. Sudden bright flares, X-ray bursts, magnetic field twists that signal an impending ejection. But solar weather is unpredictable, and we're overdue. Some models suggest we're entering a more active phase of the solar cycle, which means the next big one could be on its way, and we wouldn't even know until it was already traveling toward us at 1,000,000 miles per hour. So what can we do? We can prepare. We can reinforce power grids, create backup communication systems, develop solar early warning networks, harden satellites, educate the public. Because this isn't a maybe, it's a when. The sun gives us life, but it can also bring silence. And when that day comes, the world may be plunged into darkness, not from evil, not from aliens, but from a storm of light that burns too bright. We fear asteroids, but maybe we should fear comets even more. They come from the Oort cloud, a vast shell of icy bodies that surrounds the solar system like a frozen halo, trillions of miles away. And when one of these cosmic missiles gets dislodged and sent hurtling toward the inner solar system, the danger becomes very real, very fast. Unlike typical asteroids that strike Earth at around 30,000 miles per hour, a comet arriving from the distant edges of the solar system can be traveling at double that speed. That's not just twice the danger, it's exponentially worse. Because kinetic energy, the energy of impact, increases with the square of velocity. That means a comet moving twice as fast delivers 4 times the destructive force. A relatively small comet could hit Earth with the energy of multiple nuclear bombs, even more than an asteroid of the same size. But speed is only part of the story. Comets are also chemically volatile. As they approach the Sun, they begin to warm and sublimate, turning ice into gas. This creates long, glowing tails of dust, gas, and charged particles, stretching for millions of miles across space. And if Earth were to pass through that tail, we could be bombarded by high-velocity particles, microscopic debris, and even toxic gases. The result? Our ozone layer, the very shield that protects all life from ultraviolet radiation, could be stripped away. The atmosphere could be poisoned, climate systems destabilized, ecosystems shattered. And unlike known asteroid threats, comets are far more unpredictable. Astronomers estimate that the Oort cloud may contain over 1 trillion icy bodies, but because of their distant, dark orbits, we can't see most of them until they're already on their way toward the Sun and toward us. Many long-period comets are discovered only months or even weeks before they pass close to Earth. That gives us almost no time to prepare. No early warning, no time to deflect, only time to brace for impact. In 1994, we got a terrifying glimpse of what could happen when comet Shoemaker-Levy 9 slammed into Jupiter. The impacts left massive scars in the gas giant's atmosphere, larger than the size of Earth. If that had been us, we wouldn't be here to talk about it. And here's the kicker. The number of known comets that cross Earth's orbit is growing every year. We're spotting more, but we're still missing many, because they hide in the dark. They move fast, and they don't follow the same stable paths as asteroids. They are the cosmic wildcards, the silent assassins of the solar system. And yet, for all their danger, comets are also beautiful. They blaze across the sky with tails of light, inspiring myths and legends for thousands of years. They are messengers, not just of doom, but of mystery. Perhaps that's what makes them so haunting. They are stunning until they strike. There are monsters in the universe, not of flesh and blood, but of gravity and magnetism. They do not roar, they do not chase, but they can tear apart matter at the atomic level without ever touching you. Welcome to the terrifying world of magnetars. A magnetar is a special kind of neutron star, the ultra-dense core left behind after a massive star goes supernova. It's only about 20 kilometers wide, but it contains more mass than our entire sun. That alone is scary. But what makes magnetars truly horrifying is their magnetic field. The most powerful magnetic fields in the known universe. Trillions of times stronger than Earth's. So strong that they don't just affect metal, they affect the very structure of atoms. Imagine a spacecraft approaching a magnetar. You wouldn't even need to touch the surface. Long before you got close, the magnetic field would induce electrical currents in every metal part of the ship, generating so much heat so fast that the entire hull would begin to glow white-hot, then boil away into plasma. Circuit boards would fry, computers would melt, life support systems would fail catastrophically. And then the deeper nightmare begins, because magnetars don't just destroy machines, they distort matter. The atoms inside your body, the very particles that make up your bones and blood, would be pulled and stretched into needle-like shapes. Electrons would be forced into narrow magnetic cylinders. The quantum rules that govern chemistry and life would break down. Not even the molecular structure of DNA would survive. Magnetars turn reality into a horror show, bending the laws of physics into something unrecognizable. And it gets worse. Some magnetars are unstable. They occasionally release sudden, powerful bursts of gamma rays, called starquakes, when their crust cracks under magnetic stress. These outbursts are so intense they've been detected from across the galaxy. In 2004, one such flare from SGR 1806-20, located 50,000 light-years away, momentarily disturbed Earth's ionosphere. From across the galaxy, if that magnetar had been within 10 light-years of us, we might not be here today. That's the power of a magnetar. They are cosmic landmines, small, silent, and hidden in the darkness. But when they erupt, they can outshine entire galaxies. And we've only found a few dozen so far. There could be hundreds of thousands in our Milky Way, waiting. The only good news? They're rare. But in a universe of 2 trillion galaxies, rare still means everywhere. So why do we study them? Because magnetars test the boundaries of what matter can endure. They teach us about quantum mechanics, relativity, and the deepest rules of existence. They are nature's laboratories, deadly, beautiful, mysterious, and ultimately, they remind us how fragile we are. In a cosmos filled with extreme forces, it's easy to believe we're insignificant. But in the face of such cosmic terror, we continue to observe, learn, and understand. And maybe, just maybe, that's our greatest strength. What if the universe doesn't end in a fireball or a frozen void, but in a violent unraveling of space itself? This is the terrifying scenario known as the Big Rip, a cosmic apocalypse in which everything, from galaxies to atoms, is torn apart by the accelerating expansion of the universe. It starts slowly. The universe is already expanding. We've known that for a century. But recent discoveries show that this expansion is speeding up, driven by a mysterious force we call dark energy. And in the Big Rip theory, this dark energy doesn't just accelerate expansion. It accelerates without end. First, the gravitational bonds that hold galaxy clusters together would fail. The great cosmic cities of the universe would drift apart, slowly at first, then faster and faster, until no galaxy could see another. Each would float in total isolation in an ever-expanding void. But it wouldn't stop there. As expansion continues, it overpowers the gravity that holds individual galaxies together. The Milky Way, our home, would dissolve. Hundreds of billions of stars would scatter across the darkness, each fleeing the center at increasing speeds. And still, the acceleration would continue. Soon, solar systems begin to unravel. The gravity that holds planets in orbit would be overwhelmed. Earth would drift away from the sun, then from the moon, then from everything else. The solar system, gone. But even then, the ripping isn't done. Next, the force of expansion becomes so great it starts to disrupt individual planets. Tectonic plates split, atmospheres detach, mountains stretch and crumble. And finally, the last stage, the atomic scale, the strong nuclear force, the fundamental glue that holds protons and neutrons inside every atom, is no match for the expanding fabric of space. Atoms themselves are torn apart. Matter ceases to exist in any recognizable form. Reality breaks down. All of this happens in sequence. Galaxies, stars, planets, atoms, ripped apart by the ever-growing expansion of the universe. Time, space, and physics themselves unravel. According to some models, this could happen 120 billion years from now. But it might come sooner, depending on the nature of dark energy. And the most chilling part? We're not sure what dark energy is. We don't know if it's constant or getting stronger. If it's increasing, even slightly, the Big Rip is not just a possibility. It's inevitable. And no force in the universe, No black hole, no neutron star, no alien technology could stop it. So why do we explore such a terrifying end? Because understanding how the universe might end teaches us more about how it began. And in that knowledge, we find something beautiful. We live in a rare moment, between a beginning of fire and a possible end of fragmentation. A universe of structure, of galaxies, of stars, of life. It will not last forever, but for now, we are here. And while we are, we must look outward, not in fear, but in awe, because even the most terrifying truths about the cosmos are still part of the story. Our story.